This video is a review of the t-test. The one-way analysis of variance compares the mean values of two or more groups. The t-test is a special case that has exactly two groups. We'll start with a review of the t-test, and then later modules will discuss what changes when we move from two to more than two groups. The t-test protocol begins with visualization and proceeds to statistical testing, then estimation of the effect size, then finally the clinical interpretation. In this video, we'll walk through the protocol. The first step is visualization. A straightforward approach is to create box plots for both groups. You want the mean to be within the main box, ideally near the value of the median. Moreover, you don't want to see a lot of action outside the main box. In other words, you don't want to see a lot of possible outliers. You need both groups to behave well in order to proceed. This slide gives the standard formula for the t-test. It's a signal-to-noise ratio with the signal in the numerator and the noise in the denominator. Put a bit more precisely, the signal is the difference between the observed group means, which estimates the difference between the true but unobservable means. The noise depends on two things: the intrinsic variability of the data, represented by the standard deviation, and the sample size. Noise is sometimes called the standard error of the difference between the group means. As the sample size increases, the standard deviation doesn't change, but the standard error decreases. Turning to the statistical test, the p-value is derived from the t-distribution. To make the calculation, you have to know which version of this distribution to use, which depends on something called degrees of freedom, which in turn depends on sample size. As the sample size becomes larger, at least 30 or so, the t-distribution becomes virtually indistinguishable from the normal distribution. Because it's easier to draw, the picture illustrates a calculation of a one-sided p-value. Most statistical tests are two-sided. Please see the video on the anatomy of a hypothesis test for details. That video also walks you through how to make a simple power calculation. After the statistical test, the next step is to calculate an effect size and a confidence interval. Typically, the effect size is estimated as the absolute difference between the group means, but sometimes it's divided by the standard deviation in order to put it on a standardized scale. We'll go with the absolute difference here. The 95% confidence interval is centered on the observed difference between the group means and is plus or minus 1.96 standard errors. R will calculate this for you and bases its calculation on the regression parameter and its standard error. This will be discussed in another video. To obtain a clinical interpretation, first divide the possible results into areas of no difference between the group means, trivial differences, and large differences. For example, suppose the outcome variable is a measure of physical function, and the groups to be compared are an intervention and placebo, with positive values the difference favoring the intervention. The value of 0 corresponds to no difference in outcome. If the p-value is greater than 0.05, the 95% confidence interval with the difference between the group means contains 0. Everything to the left of 0 suggests that the intervention is worse than the placebo. Numbers to the right of, but very near 0, suggest that the intervention is only trivially better than the placebo, presumably that the outcomes aren't different enough to merit the cost and hassles of the intervention. At some point, the intervention becomes significantly better than the placebo in a practical or clinical sense. That's where you draw the line, and you call that point the minimum clinically important difference. The next step is to compare the effect size and its confidence interval with the regions that you've just created. First, ask whether or not the point estimate, which is your best guess of the impact of the intervention, falls within the region of clinical significance. Then ask whether the entire confidence interval falls within the same region. If so, the results of the study can be considered definitive. Please note that as the sample size increases, the width of the confidence interval decreases, and it's more likely that your study will yield definitive conclusions. As drawn here, the study isn't definitive. Some of the points in the confidence interval exceed the minimum clinically important difference, but some fall to the left of that difference. I'll conclude this video with a quirk that has needlessly confused students over the year. A t-test truly is nothing more than a special case, the one-way analysis of variance. After you use R's t-test function to perform the analysis, you'll discover that there are two versions of the test, one of which assumes that the variances in the two groups are equal and another one which doesn't. You won't find a similar distinction in the function used to perform the one-way analysis of variance. That function always assumes that the variances among the k groups are identical. It's usually as much ado about nothing. Both the t-test and the one-way analysis of variance perform well so long as the variances among the groups aren't dramatically different. Here, dramatically different means differs by a factor of 4 or more. If the variance differs by this much, it'll become apparent to you during your initial visualization of the data. Moreover, the proper response to this problem will often become apparent as well. Possible responses are discussed in another video.